present. Why don't I try this? Okay, so in the ongoing adventure of trying to communicate information remotely, I'm going to try this. So I'm presenting, and hopefully people can see. If you type anything in the chat, I think everyone has their mic muted, which is good. Maybe the TAs can keep an eye on the chat, and if there's any questions that need to be answered, the TAs can help me. So the first thing I wanted to do was call your attention back to the Fibonacci sequence, which we had talked about last time. Let me go get a bigger font. Let me grab like 18. So hopefully this is readable. So every Fibonacci number, like 5, is the sum of 2 plus 3. And the next one will be 8, because 8 is the sum of 5 plus 3. And the next one is 13, and 13 is the sum of 8 plus 5. So these type of sequences come up a lot in mathematics, and we often describe them using something that's called a recurrence. So a recurrence is just a formula that tells you how to compute the next Fibonacci number, like the nth Fibonacci number, using the previous Fibonacci numbers. So we need like f0 is 0 and f1 is 1, and then for this is like for n greater than 1. So recurrence is just a way of expressing an infinite sequence by telling you through a formula how to compute the next term. So similarly, one of my favorite recurrences is, so let's say, it would help if I could spell. Let's say that S0, so S1 is equal to 0, and for n greater than 1, you use the formula Sn is going to be the previous one in the sequence plus 2. So this formula tells us, this recurrence formula tells us that we start at 0, and then that to get the next term, to get the next term, all we do, add 2. Right, this is my add 2 sequence. 4, 6, 8, 10, 12. So this recurrence generates this pattern. So I guess first of all, are there any questions about like the way these formulas work? Do these type of formulas make sense? Is that kinda? Okay. Okay. Yeah, so if there's anything that I can say to, if there's anything that I can say to help make this more clear, please let me know. So one of the things that I just wanted to highlight is that these recurrence formulas lend themselves very well to recursive functions in Python. So I actually don't know how much recursion you saw in intro Python this year. It varies sometimes year to year depending on the schedule. But a recursive function is just a function that calls itself. So a recursive function is a function that calls itself. So in the middle of the function, you go and call the function on a different input. So like s of num let's say, if num equals 1, return 0, else. I hate this auto capitalization. I wonder if there's a way to turn that off. Else return s of num minus 1 plus 2. So this Python code matches up perfectly with this. This Python code matches up perfectly with our recurrence. So the recurrence says that the first term in the sequence is 0. So my Python code says if somebody asks me for the first term in the sequence, I return 0. And if someone asks me for a different term in the sequence, I go and figure out the previous term and then add 2. This is a function that okay. Excellent. So one thing that's probably pretty obvious here is like this sequence is a pretty easy sequence, right? Like if somebody asks me what is the 10th term in the sequence, I could go and run the recurrence and I could say, okay, if you want the 10th term, first I'm going to find the 9th term and then I'll add 2. And to find the 9th term, I need to go find the 8th term, and then I'll add 2. And then to find the 8th term, I need to go and find the 7th term. So this recurrence relation shows me how I can work backwards. And like to find the 10th term, I go look at the previous one. To figure out that one, I look at the previous one. To figure out that one, I look at the previous one. And this is more work than necessary in order to compute the like 10th term or nth term in the sequence. Many recurrences have a we call this a closed form solution. Closed form solution. So for this previous one that we were doing, I'm going to claim that for this relation, that the closed form solution is actually S sub n is, let's see, 2 times n minus 2. So I'm going to claim to you that if I wanted the like the first term or the 1, 2, 3, 4, 5, 6, that the 6th term is just 2 times 6 minus 2, like 12 minus 2. So like it works for 10. Here, this is the 3rd term. The 3rd term is like 2 times 3 minus 2, which is 4. So yeah, this seems to check out. So if I go do random checks again, like maybe there's like this 8, this is the 1, 2, 3, 4, 5th term. Plug in 5, 2 times 5 is 10, minus 2 is 8, which is exactly what we had here. So my claim is this formula describes the same sequence as the recurrence, recurrence above. So, I mean, it seems to check out, but there's an infinite number of terms in the sequence, and yeah, there's an infinite number of terms in this sequence, and I can't really just check it out for every particular term. Which means that basically, if I wanted to convince you that if I wanted to convince you that this formula is the same as the recurrence, that this formula is a good formula for this sequence, I would need to use induction. So the substitution method, recurrences. So the substitution method for solving recurrences is basically basically guess and check. Yeah, so this is basically like guess and check, and you use induction to verify that it works. So if I was going to use induction to show that this formula works with this recurrence, that these are like the same thing, in order to do that, I would first check the base case. So the base case for my recursion, or my recurrence, is that the first term is 0. So the base case is going to be like the 0th term in the sequence should be, according to my formula, 2 times, I'm sorry, 1. Base case is 1. 2 times 1 minus 2, which equals 0, which is indeed okay, victory. Okay, so then next step for an induction proof is induction hypothesis. And so we assume the formula works for n equals k, for some k, right? Then let's see. Inductive step is to go and this is why we call this the substitution method, is because the substitution method for recurrences, your inductive step is just substituting in to this formula. So the inductive step is, we know that S of k plus 1 is S of k plus 2. By hypothesis, S of k is what this n time, wait, what was this? 2 times n, or 2 times k minus 2. So what we're doing here is we're substituting our formula in as our inductive step. So S of k plus 1 equals S of 2 times k minus 2 plus 2, which is 2 times k plus 2 minus 2. This is just rearranging things, which is 2 times k plus 1 minus 2. So the formula works for k plus 1. And so all we did here to verify that this formula works for this, this formula works for this recurrence, all we did is we substituted in the formula. I mean, we checked the base case, obviously, because checking the base case is important, but then we just went and substituted in the recurrence for s of k plus 1. We substituted in the formula for s of k, and that's why this is called the substitution method for recurrences. There's something in chat. Okay. Yeah, so I'm definitely going to share this Google Doc. And I think that being able to move back and forth between programs and recurrences is important from a like mental gymnastics point of view. So this so this recurrence is, I mean, this is just like in some sense shorthand for a program. What I'm doing here essentially is I'm trying to convince you that if we wrote a program based on this recurrence, that it would always return 2n minus 2. But I will share this. So I'm trying today, again, I don't know what's going to be useful, but I'm trying today to record our discussion, and then I'm also going to share this this document and see how it goes. I just want to work through one more example, and then I'm going to encourage you to try to work on some things by yourself. But I wanted to try one more example, which is a recurrence, new example. T of 1 equals 1, and for n greater than 1, T of n equals 2 times n minus 1 plus, T. So what this says is if somebody asks you to compute the answer for n, what you do is you go and figure out 2n minus 1 and add that to the previous term in the sequence. So the first term in the sequence is 1 because of the base case. So this is the base case. And again, if you're writing a program, this is the termination condition for this is how you know when to stop if you're writing a program. So this is 1. And then this says for the second thing, for n equals 2, this is going to be 3. So this is going to be 3 plus 1. And then the next one is going to be so this is 1, 4. So this is going to be 5 plus 4, and this is going to be 9. And then this next one is going to be 9 plus 7, and that is 16. And then 11 plus 16. Is 20, right? No. 9, so this is, plus 9 is 16, and then 16 plus, helps if I do this right. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is this is 9 plus 16, right? Because it's 2 times 5 is 10. 10 minus 1 is 9. So 9 plus the previous thing is 16. which is 25. Okay, one more and then I'll be done here. So now this is 6. So 2 times 6 is 12 minus 1 is 11. And then I add the previous thing, which is 25. So then my next term is 36. So it kind of looks like this sequence 1, 4, 9, 16, 25, 36, that seems like the squares. This seems like T of n is just equal to n times n, or n squared. So again, this is just a guess. We've only checked 6 different possibilities. There are infinitely many possibilities that, I mean, for all I know, somewhere off on this side of the page, if I go another term, maybe this breaks, right? You always have to worry if you're trying to think about things for all possible inputs. Well, maybe there's an input that I haven't considered off here for like the 10th term in this sequence. Is the 10th term really going to be 100? I mean, I think so, because it looks like there's a pattern here, but I don't know if that pattern actually holds, or if this is just coincidence for the first 6 numbers in the sequence. So then, let me go and copy paste my substitution method. So I'm interested in the base case here is T0 equals, or no, not T, sorry, T1, my base case. T1 should be 1. My formula says that T of 1 is 1 squared. 1 squared is 1. T of 1 is 1 times 1 according to my formula, which is 1, which is actually the first term. So this actually works for the base case. And then let's look at let's look at this for, so let's assume for some k that the formula works. So okay, so this is the formula works for some k, and now let's look at k plus 1. So if we substitute, we see that T of k plus 1 is equal to 2 times k plus 1. Wait, this is 2 times k plus 1 minus 1 plus, okay, right, this is what our formula says. Our formula, if you plug k minus 1 in, you get 2 times k minus 1 minus 1, 2 times k plus 1 minus 1, and then you add on the previous term. So this is compute a new number and add it to the previous term. And this is T of, okay, so minus 1 plus. So we use the hypothesis to replace T sub k with k squared. And so this means that T plus k plus 1 is equal to k squared plus 2k plus 2 minus 1. Plus 2 minus 1 is just plus 1. And from algebra, this is k plus 1 times k plus 1. So Okay. K plus 1. So by induction, the formula always works. Okay. I will provide you all with a copy of this document in case these examples are helpful, and then I can toss this up on Canvas very soon. So are there questions on these type of like solve a recurrence by going and substituting in you're substituting in the formula for TK into the formula for TK plus 1. You go and like substitute this into this and get and demonstrate that TK plus 1 is what the formula says it should be. So are there any questions on this? Seeing no questions at the moment,
I think Nat asked a question.
I'm sorry, who asked a question?
I did.
Oh, I'm sorry. Oh,
that's all right. I was just a little confused on how we converted the first part of the formula to the part that had k squared.
Okay. Yeah, so this is, no, thank you so much. I really appreciate you asking these questions. Also, I don't know if this is always obvious to you as students, but anytime you ask a question because something doesn't make sense, there are at least 4 other people on the call who are wondering about the same kind of thing. And so it's really nice when you can articulate a question. This is, we have our formula. So we have our formula, and what I'm doing, let's see, which, Natalie, what part of this was,
okay, so Tn is the same as n squared.
Well, so this is my claim. So this is the definition of Tn right here. This is our function that is telling you how do you compute Tn. So this is something you could turn into a program. This would be like, you know, on input n, compute this thing, and then add it to t of n minus 1. This is what is defining the sequence, and my guess is looks like a pattern. So when I look at the numbers 1, 4, 9, 16, 25, 36, this looks like just like numbers squared.
Yeah.
So I'm just guessing that this is true. I'm guessing that if you wrote this recursive program, that program would be the same as just take the input and square it. That you don't need to go and like do all of this work of take 2n minus 1, then go compute the previous one, then go compute the previous one, then go compute the previous one. I think this is an easier way. I'm claiming that this is an easier way to compute the same thing.
Okay, yeah.
But,
so you're just simplifying it by finding the pattern.
Yeah, so I'm simplifying it by finding the pattern, but then the substitution method is used, this induction method is used to demonstrate that the pattern actually works. Like, if you had, let's say you had code that did this, and I came along and said, hey, your code is really inefficient. You're going and like running a lot more steps than you need to. You could replace your function with just take the input and multiply by n. And naturally, you should be a little skeptical of my like cutting corners and be like, hey, is this really going to give me the same answer? I know my customer is happy when I give these answers. is my customer still going to be happy if I just like square it, or is that shortcut going to give me some weird numbers that are not helpful to my customer? So I'm trying to show you like, hey, the shortcut is actually a good shortcut.